Good morning all of you. Today we will be studying about the topic tangents to a circle. You all are familiar with the term circle and various terms related to circles. Now what is a circle? A circle is the collection of all the points which are at a fixed distance from a fixed point. And this fixed point is known as center and this fixed distance is known as radius. Now there are terms which are related to circles which we will be studying in this chapter. First of all, let's recall about the term chord. What is a chord? A chord is a line segment that touches the edges of the inside of a circle. The greatest or the longest chord of a circle is known as its diameter, and the diameter goes through the center and is equal to 2 radii. Now let's move on to the next term that is associated with circle is secant. What is secant? A secant is a line touching the circle at 2 points. As you can see in this particular figure, the line intersecting the circle at 2 points is known as secant. Now, we next come to the term tangent to a circle. The word tangent comes from the Latin word tangier, which means to touch, and it was introduced by the Danish mathematician Thomas Finnecke in 1583. Now, what is tangent? A tangent is a line or a line segment that touches the circle at exactly 1 point. So, this is the basic difference between a chord, a secant and a tangent. A tangent a chord have its endpoints on the boundary of the circle. A secant is something which is passing through the circle, intersecting the circle at 2 points. And a tangent is something that is touching the circle. It's a line or a line segment touching the circle at exactly 1 point. And this point is also known as point of tangency, or this is also known as point of contact. As you can see in this particular figure, there is a wheel and this yellow line represents the tangent. And you can see that tangent is perpendicular to the radius at the point of contact or at the point of tangency. Now, tangent to the circle is a special case of the secant, where the two endpoints of its corresponding chords coincide. In this particular figure, please focus on the line segments PQ1 and PR3. If you focus at them, then these are the two chords or these are the two secants that are intersecting at the point P, and thus their tangent is passing to a point P. So we can conclude that tangent is a special case of a secant. Moving ahead, now what we have, concentric circles. We have seen concentric circles around us, and the concentric circles are the circles which have the same center, just with the different radii on the same plane. As you can see in this figure, there are so many circles drawn with the same center but with different radii, like the target board for a player who is playing shots. Now there are different type of tangents to given circles. First you can see the interior common tangents that would go through a line segment drawn from the centers of the two circles. You can see here there are two figures whose centers are M and O. And the two tangents are passing through the point A, which is at the line joining the two centers. So such tangents are called as interior common tangents. Now in this figure you can see common tangents or the exterior common tangents that are not crossing the segment between the centers of two circles. Now in class 10 syllabus we have two very important theorems based on the tangent. This is theorem 10.1 from your NCERT, and which you usually get in your board exams. The tangent at any point of a circle is perpendicular to the radius through the point of contact. Now we need to prove this theorem. Let's see how to prove it. We are given a circle with center O with tangent xy at the point of contact P. Now what is to be proved? We need to prove that OP is perpendicular to XY. Let's start the proof. Let Q be a point on XY. Then connect OQ. Suppose it is touching your circle at the point R. Now you can see here OP is equal to OR. The reason for this the same is that these are the radii of the same circle. Now OQ would be equal to OR plus RQ, as you can see. Now in place of OR we can also write OP. So OQ is now equals to OP plus RQ. So from here we can generalize that OQ is greater than OP. Similarly OP will be smaller by any other line segment joining the center of the circle to a point lying outside the circle. So OP is the smallest line, and the smallest line is always perpendicular. Therefore we can conclude that OP is perpendicular to XY. So thus the theorem is proved that the tangent at any point of a circle is perpendicular to the radius through the point of contact. Moving ahead with theorem 10.2 of our NCERT, that says the lengths of tangents drawn from an external point to a circle are equal. You can see, let a circle with center O and P be a point outside. Then P, Q and P are the two tangents to a circle intersecting at point P, at point Q and R respectively. Now what is to be proved? Here we are supposed to prove that PQ is equals to PR. How can we prove that? Let's have a simple construction over here. Join OQ and OR and also join OP. Now you can see two triangles, triangle PQO and triangle PRO. In these two triangles, let's have three common corresponding elements. OQ is equals to OR, the reason being the radii of the circle. OP is equals to OP, common, and angle PQO being equals to angle PRO. Both these angles are equals to 90 degree, as we have proved in the first theorem. So by RHS congruency criteria, these two triangles PQO and PRO are congruent. Therefore PQ is equals to PR by CPCT. Thus we have proved that the length of tangents drawn from an external point to a circle are equal. Now we would be using this theorem to find the unknown quantities and to prove a given condition. Let's proceed. Solve for x. You need to find the value of x in the given question. Let's see the solution. Now here in this figure, these are the two tangents drawn to a circle with a common external point. Therefore these should be equal. Therefore 3x plus 14 is equals to 5x minus 8, and when you solve this linear equation, you'll get the answer of x equals to 11. Similarly, you can find such other cases. For example, here in this figure you have to solve for y. Here also we have been shown two tangents to a circle from a common external point, so these have to be equal. Y square minus 7 is equals to 18. Mentioning the reason, length of tangents are equal. Solving this equation will get y equals to 5 units. Now please, we are moving ahead to a bit complex proving question based on the similar concept. The question says a quadrilateral ABCD is drawn to circumscribe a circle. Prove that AB plus CD is equals to AD plus BC. Now in this figure, let the circle touch sides AB, BC, CD and AD respectively at points P, Q, R and S. Now we can see from point A, the length of the tangent AP is equal to AS. Similarly, from the point B, the length of the tangents are equal, that is BP is equals to BQ. From point C, the two tangents CR and CQ are equal. From point D, the tangents dr is equals to ds. Now if we add all these four equations, we'll get AP plus BP plus CR plus DR is equals to AS plus DS BQ plus CQ. Now when we add these, we result in AB plus CD is equals to AD plus BC. So if a quadrilateral circumscribe a circle, then the sum of the opposite sides is equal. Now let's see the concept map of the given chapter. You know what is a circle? A circle is the collection of points in a plane which are at a constant distance from the fixed point. As we discussed earlier, this fixed point is known as the center and this fixed distance is known as the radius. Now, there are three basic terms associated with the circle: chord, secant and tangent. A chord is a line segment having its endpoints on the circle. A secant is a line that intersects a circle at two different points, and tangent is a special case of secant. It has only one point touching the circle and that point is called as point of contact. Now, since the distance between the center of the circle and the point of contact is the smallest line segment, therefore the radius is always perpendicular to the tangent at the point of contact. Then moving ahead, we have the theorem that we have proved that in a circle, the length of the tangents drawn from a common external point are equal, which can be proved easily by applying congruency theorem. Now you can move on with the similar type of questions and we'll discuss them later. Thank you.